Again, my name is Dr. Mark Hodges. I'm an astronomer here on site at the Observatory. I've been here 39 years, and I've worked on every project on site. So feel free to ask any questions that you might have, and I'll try and answer.
Did you grow up there? You look real young.
Well, I'm 70 actually. And my wife wants me to retire so I can spend more time doing things at home, do the honeydew. Honeydew list is getting longer and longer. We're going to start by going up to the 40-meter telescope, up to the catwalk, and we'll look around the site, and I'll point out the different instruments around the site. The west end of the observatory, which is not really very easily visible from here, it's 3/4 of a mile away, and that's where most of the offices, the welding shop, auto shop, and that kind of stuff is. But most of the observing is done out here with the telescopes out here. Okay, let's head over to the telescope.
Okay.
It's a copy of the fun facts about the telescope. People ask the same, we're asking the same questions every time I give a tour. And so I finally created a full page of fun facts about the telescope. Answer most of the questions people have. Like how much does it weigh, and when was it built, and that kind of stuff. The telescope was in operation 24 hours a day up until about a month ago, when the generator, we have two motor generator sets, one for each axis. And the generator, one of the bearings went out, and we had to send it in for repair. And it just got back, and the guy that does all the maintenance for us is in the process right now. I can see his truck over there. The process of replacing the generator, putting the generator back in.
I wondered what was going on. I saw a front end load over there.
Yes, it's a heavy generator.
Is this dish part of the VLBI?
It was, in fact, that's what I was hired for back in 1984, was to do VLBI with the 40-meter telescope. And we stopped doing that about 1991 when the VLBA instrument was built.
Oh, so that's VLBI.
Yeah.
That's what, 10-meter dish you're doing?
No, I think that's a 25-meter dish.
Yeah. I have a question before we go any further. Why do we have this on a railroad track here?
There's a little history, a little story about that. Before the VLA was going to be built, they had a meeting at the Office of Naval Research, and there were actually three different ideas. One was to build a 300-foot class instrument. One was to build an array of 830-foot telescopes, and the third was to build an array that eventually became the VLA. But the decision was made initially to build an array of 830-foot telescopes, and Caltech got money to build the first one. And while this one was being built, they had another meeting, and they said, it's a lot of money, we better have another meeting, make sure we're making the right decision. And then they finally, okay, we're going to build 830-foot telescopes. Well, right after they made that decision, radio astronomy funding, instead of coming from the Office of Naval Research, then started coming from the National Science Foundation. And what the first thing they did was they said it was a lot of money, and so they decided to have another meeting, and at that point they decided to build the VLA. So this was going to be one of 8 elements, and if it's not going to be an interferometer, there'd be no reason to put it on rails. So it's been clamped on the rails actually, and we did a lot of crustal dynamics work back in the 1980s, and a variety of other science projects. The most important of which I think with this telescope was they measured the smoothness of the microwave background radiation to about 1 part in 500,000. If they could have done a factor of 2 better, they would have seen fluctuations in the microwave background itself. But that was actually first done from space. And so we just missed out, but we did at the time, before the measurements were made with this telescope, there was something like 70 or 75 different theories of the early universe. And because we showed it was smooth, the microwave background was smooth to 1 part in 500,000, that eliminated all but 5. So that's probably one of the most important things this telescope has done. But in recent years, we've been measuring fluxes of radio sources, a few thousand of them, and we do them on a regular basis. And they found some very interesting things. We found some supermassive black hole binary systems. We've seen what we believe to be gravitational lensing at radio wavelengths, which is hadn't been seen before. So there's a variety of interesting things we've discovered with just the observation with this telescope. Right now it's using a receiver that operates at roughly 13 to 18 gigahertz. So it's a fairly short wavelength for this telescope. Much shorter, and then the efficiency of the telescope goes way down. And if the wind blows over about 20 miles an hour, 20, 25 miles an hour, the telescope will go to a stow position because the data starts getting a little noisy and it's hard to drive system.
Notice you got a big Westinghouse up on.
Yeah, they were the principal contractor. So we're going to go into the control room.
I think you're headed into a Faraday cage. Okay, we
Digitizers in them, and we divide the signal up so that each approach can handle 500 megahertz in the spectrum. We go from 12.8 to no. Yeah, I think it's 12.8, 17.8. This is no 13.2 to 17.8 gigahertz. So we have separate LOs, and so each band covers 500 megahertz, and all gets digitized, stored, and we can analyze that data later because the way we fire the noise diodes actually work. And a separate back end in the receiver itself that does analog, but it overlooks the entire data. So most of the science that we've done so far is all been using that analog.
What's your timing source for this?
We have a GPS receiver. The thing linking up there once a second, and
That's good enough for you to do.
yes, single dish. We do get a 10 megahertz. We still use the old control panel, and so if the telescope were operating right now, I would put it in manual mode, and I could drive it in acid for speed. Same angle from the elevation. Put it in computer control with the edge. I can put it in acid angle mode, and drive the cabinet. Move the telescope up there, it gets a line, and we're adjusting the limits. So, in straight up, service down the horizon, go up, and look up. And then put in, we have these resolvers, but they over the years they've gotten very noisy. So unless I really need them, I don't plug them in. Just sit and make them noise. But they are a nice backup. Our captain for
So they're in manual mode and this is the thing. How do you know where you're aiming?
I have a display here that uses the
Well, it's not on right now. So, oh, that makes sense.
So we have a display here showing different monitor points, so I can actually look at something. I can actually create a plot of any of these, and it shows what the azimuth and elevation are.
But what's your steering at? Mechanical steering.
The encoders go down to 5 arc seconds, but when we create a model, pointing model for offsets and everything else, and we find that over time the model degrades. We don't know exactly why. So about once every 4 to 6 months, something like that, we'll peak up on different point model. Okay, what was the offset? Thought it should be this. When we're looking at that sky, and find out what those are, do a parameter, and get the pointing offset. And of course, really, really well for the first few weeks, and it slowly degrades. But if you can peak up on a fairly strong source, it doesn't really matter. You want to get to the point where the beam itself is looking at that source fairly strong, and then you see up on that source. So you don't care if it's not looking directly at it. Oh, yeah, we have preload in azimuth and preload in elevation. Yes, sir. Shaft encoders. And, yeah, these are the actual shaft encoders, and 21 bits. And this is the unit that reads it to we go 10 times a second. Milliseconds, we get a reading back to the encoder. And if any of the bits look wrong, it immediately throws an error, and it says telescope's moving too slow or too fast. Well, I know a telescope's not moving too slow or too fast. This and per year, cryogenic compressor for the helium compressor way up high, crane with the extended jib to get it high enough, and it was we call it a truck crane. Actually, you can drive the crane down the road like a truck, and got to be at a point where it was dangerous. So what we decided was put the compressor on the ground with the telescope. And it comes up at 300 psi and goes down to about 60, 70 psi per year. This cable in the middle is the fiber optic cable. We have 12 fibers in there, and we use 2 of them for Ethernet and 1 for our signal coming back. So we've got a couple of spares. The cable wrap system for azimuth, the cables wrap around a big drum, and then come over a shift up there, and then these just hang there. Slack. Well, they've gotten rid of most of the. These are kind of hidden, and so it's stretched out to a certain point, and it hasn't really changed a whole lot. When I first came here, about once a year, this end would touch the floor, and then it would fall out of a big bag. But right now, we don't use this for much other than power, because the helium and fiber does information. This is cool. Yeah, it is. So what's your thesis? Let's see. Thesis on this guy is around 30. Not fantastic. This particular receiver has 2 beams, and breadth, and we switch between them on the sky. So in other words, we do a measurement on source and off source, and take the difference. And the actual procedure is to do an off on on, off. We want a symmetric procedure because if you do it on and off, you have a drift in your system. You're not going to subtract, you're not getting exactly the right answer. So even though you're switching between beams, which helps, really helps to have a symmetric procedure in time. When you do that,
How often do you do that?
we're doing it constantly. Yeah. The telescope's doing a lot of moving. Not very far in the sky, the beams are separated by about 7 arc minutes. But that's how we get there. Very good flux measurements. And then, of course, we have standard sources that we look at that we know that are very stable and aren't changing in time. Use those to help calibrate to make sure everything's moving.
Is that like the VLA list or something that I've seen?
Well, I don't know what the is.
They've just got a list of endless calibrating knowledge.
Well, yes, many of them are the same, but we finally, everything's variable to some degree, and so we've picked a couple of sources: 3C286, 3C161, AGC 7027 is pretty constant. We have a few that we'd like to look at, but we typically will calibrate just on one, call that our fundamental, and then compare everything else. Other things are drifting, and that was not, we know there's a problem, but a straight line for everything, and we know that things are working properly. When we have to work on the receiver, we take a telescope around to the south, all the way down, and when you open that door, there's a walkway that takes you through the vacuum structure, you open the door to the dish, and then you go up the lower feed like this. And if I have to stand on the hand, if I have to change the receiver, it means I have to stand on the handrails. The first time I went out, it took me 5 times. I couldn't, I just couldn't, I'm too afraid of heights. And so I turned around and come back. But now I'm to the point where I'm still afraid of heights. But as long as I don't look down, I'm okay. I stand on the handrail, and of course I use the safety harness. And myself in, and I can hold the receiver because I'm concentrating on the receiver, not on where I am and how I am and all the time. So.
The warning sign on the door didn't help.
Well, that's actually, happened after there was an accident.
Oh, is that right?
That's all.
Oh, yeah. Oh, wow.
So, at that point, they start getting very concerned about safety.
I was just thinking, it's a warning as you're going out there, it doesn't really help your state of mind as you're.
I know, you're right. And the padlock is pretty cool. I mean, it's a side padlock.
Yeah.
So, anybody with a key. Yeah. All right, let's meet the aspect right. Telescope has 2 10 horsepower DC motors. One of them for azimuth is located right over. The gear reduction is 43,201. So the motor's got to turn around 43,200 times. Telescope once. Backing structure is made of more than 4.5 miles of 4.5-inch steel pipe, and you can tell immediately that it's steel because you can see rusty spots in it, and it's in need of being repainted again.
You have to adjust the counterweights when you read.
Yes, actually, we probably should.
I think you mentioned that.
How do you keep the birds from looking in here?
I don't want to make that public.
Okay.
Where there's a dormitory, a cottage, our kitchen, most of the offices are down at that end, auto shop, welding shop. We also have a boneyard for stuff that we want to keep, but don't want to throw away just yet. Down here to the due west of us are the 2 90-foot telescopes, and the closer one is considered too dangerous to use again because there was a design error. They thought they could leave the pipes in the backing structure open, and it wouldn't be a problem because it rains in there. When you tilt the telescope over, it's all going to run out. Well, what they didn't realize is birds nest in there, and the water goes in, and it stays humid for a lot longer. And so it ended up getting a lot more rust and and losing the wall thickness on the backing structure. So we probably won't ever use that closer 90-foot dish ever again. The one that's further on is still being used. It's used as a calibrator, or it helps to calibrate the solar array. I'll show you first. And so what they did was they took them in, divided it up into 3 parts, and put each part on a flatbed truck and shipped them down to Arizona because they're too large to travel fully assembled like this. These 3 were purchased by people doing the Event Horizon Telescope in Massachusetts, and they hope to come out, let's see, in a couple weeks, I guess, and check these surfaces and make sure the dish surface is accurate enough for doing the millimeter observations that they want to do. We can see one of the DSA dishes here that's headed for assembly, or not assembly, for installation in the array. The crew is busy working on other stuff right now. So as soon as they have time, they'll be putting more dishes out in the array.
I have a question for you, Lee.
Yeah.
Were these originally part of the Paul Allen array?
Yes, they were. Oh, no. Yeah, they were at Hat Creek, but they weren't part of the Allen Telescope array. No. Those look a little bit. Yeah, these are can work down to wavelengths as short as 1 millimeter. We have the Deep Synoptic array, which are these tan colored dishes. We have right now 63 of them in operation. It looks like one over here is not quite behaving properly.
Okay, so supposedly the half the crew went up a vertical ladder that the other half did not want to try. Schedule this stuff. How do they allocate time?
We have a kind of a set number of sources that we look at, and they've been given category A or category B status. And so we try really hard to look at all the category A radio sources twice a week. And the B ones might get looked at maybe once a week or once every other week. The computer program that generates the schedules actually goes through and figures out optimal organizing of which sources and so forth to look at. The reason that they don't use the same schedule week after week is the fact that they don't want to observe near the sun.
Oh, yeah.
So that means a whole new set of schedules every week.
Where's that schedule at? Is that here or is that in Pasadena or something?
Well, right now, the gentleman that creates the schedule, they decided I was too busy to take my time to create the schedules because it does take a little while. We have a gentleman that's in Crete, and he's part of our group.
Wait,
and,
Crete like country Crete?
Yes, the island.
Oh, the island, yeah.
And he creates the schedules and makes them available. He puts them on the computer here, one of the computers down in the base that we're looking at. And then I actually implement them. There's 3 schedules a day, and of course 7 days a week, so there's 21 schedules.
How far off the sun do you stay?
We don't observe any 10 degrees. 10. We want no closer than 10 degrees from the sun. They only move in one axis, and there's a horizontal axis, so they only move along.
Does each one have its own GPS, or how do you know where it is? Or do you need to know that close?
Physical location on the Earth relative to each other.
Okay.
And that's just a constant. It never changes because these are bolted down and never move. They have 2 orthogonal linears that are picked up with a amplifiers that Sandy Weinrep made at Caltech. They're like stated, very low noise. Yeah, great amplifiers. So it really makes it. We have in fact, it's almost too sensitive in the systems. We're very sensitive to interference, and so things like cell phones, spacecraft, all kinds of things will create noise that really will. yes, they have ways of getting rid of false triggers, so they analyze the data very quickly. And I'll keep back into that. Any more questions?
Wasn't filming you actually. Could you go over this one more time? Real quick.
Sure. The optical signals from the antennas come all the way in here. Each box is for a particular antenna. It doesn't have to be in this particular location, but it was. We just decided to do it. I decided to do it because I was the one at the time that was building it. As the antennas got built, I would put a box in and label it for that antenna, and then just let them know that this cable is talking to this antenna. And the optical signals from the antenna come in here. They get converted to an electrical signal in a fiber optic receiver. Then we monitor that power, mix it with a common local oscillator signal. If the optical power looks good, these LEDs are on. And the IF after mixing is right here. We can monitor the IFs if we wish for troubleshooting. If the IF power looks okay, then we have these red LEDs. And again, I don't know why they chose the particular LEDs that they did, but it's kind of neat. You can shut the lights off and these generate enough light you can easily see. The IF comes out here, and we put pads on here because we found the cables had standing waves on them, producing a lot of ripple across the pass pad. It wasn't real important to get rid of, but it was nice to have a smoother pass band that feed into the snap boards. So it comes out here on coax, goes up overly, goes into the snaps, and each snap can handle 6 inputs or 3 antennas worth of information. And there's 10 boards in a chassis and 4 chassis. And the output of the snaps then comes on these 10 gigabit optical interfaces, and they feed a 40 gigabit switch. So that 40 gigabit switch then can communicate with all the servers that we have on the other side of the meat locker curtains.
Well, Mark, that's a DJ's word, right?
They have A to D.
I'm sorry.
Yeah, they have A to D's built into them.
Right.
The Snap 2s that are out in the LWA, we made our own digitizers for it because there was no commercial one that was going to fit this particular form factor that we have for the Snap 2s.
But
So
when they come out of here, though, it's digitized. Up until here, it's analog.
It's analog until it gets to here. Now it's digitized. Well, we've got a lot of information to send, and so it's on this 10 gigabit fiber.
How many bit A to D are you know?
I think it's an 8-bit A to D, but I'm not absolutely certain.
Only 8.
Yeah.
Right.
Yeah. Victor would know right off the top of his head. I don't remember anymore. But anyway, I wanted to let you know that during COVID, when I first got down here, there was nothing here. I manually, by myself, moved these racks, every one of them in here, bolted them to the floor, and anchored them with epoxy anchors. Bolted them to each other.
Earthquake, California earthquake stuff, is that what?
I don't know. Yeah, that seemed like a good thing to do. I figured out how wide do I want them. I want to be able to work in here and not be like this. You have to work out the distances and spacings and stuff like that. I did all the electrical raceway that you see in the ceiling. I did all the lighting, LED lighting. This is kind of fun.
Every cable you ran?
No, later on, I got busy doing some other stuff, and so I had somebody else actually, once I already got started, in fact, I'm not doing it anymore, and we're still adding some antennas. So as they add antennas, it's not that hard.
So,
I was a little tedious.
so graduate schools want to know, how did your PhD in physics prepare you for this assignment here?
Physics and astronomy.
Oh, and astronomy. Oh, okay.
Physics and astronomy. I don't know. I just enjoyed doing it. It was really a lot of fun because there was nobody to complain and say, I would do it this way or you didn't do it the right way. When they come down, they look at it, they just say, oh, it's good. So that was all. Yeah, it was all, there was a lot of planning involved ahead of time. But as I was building it, it was fun to do it all myself. I like how the meat lockers turned out. And I discovered these tandem breakers. So where you normally would have in the past one circuit breaker, you can actually get two now, the same size. And so all I had to do is add a few more wires, and that way I can. Each server has two power supplies. Unfortunately, they're on the same phase. I wasn't able to make them so they're on separate phases.
So your correlators, are you doing software correlators or are you doing GPU?
No. Well, there are GPUs in these
Right,
guys.
but sometimes they have just hardware.
Oh, yeah.
Banks and banks and banks of
Right.
hardware.
Yeah.
You don't do that. It's all
No,
software.
it's mostly software.
So it's not only doing the correlating, it's doing the correlating and the searching and all the post
Yep.
analysis.
Yeah, he figured out early on, Vikram figured out early on how many he needed for doing each aspect of the task.
So I'll ask you, okay, so how do you store the data?
The data is stored on what we call a RAID system. It's multiple hard disks that if any hard disk fails, it beeps an alarm, there's LEDs that flash, and we get emails that a hard disk has gone bad, and so we can hot swap. We can pull it out, stick another one in, and the system will automatically replace it. The only concern is because of the type of RAID system we have, is that if, while it's trying to rewrite everything, if it fails, we can lose everything.
Right. So you don't mirror right from the beginning. So you have two sets. I mean, some people do two complete sets.
We have, for the 40 meter data, we have three. We have one here on site, we have one on campus down in Pasadena, and another one in Finland.
Yeah, just in case.
Yeah, just in case.
So how much, like what's the capacity of it?
Varies tremendously. The one that I just installed for the LWA has 5 petabytes. 5.128.
So one drive is a...
Oh, no. There are 18 terabyte drives.
So a lot.
And we have 8 of them, and each one has 36 18 terabyte drives.
So do you store the raw data, or do you store the data that's already been correlated and processed? Or both? Because in some sense you got to store it in order to correlate.
Yeah.
But some people do more or less real-time correlation, and then once they get that, they get rid of the data.
It's too much for us to store raw data.
Yeah.
So it's after it's been processed.
Right.
Yeah.
Because there's a lot less of that.
Yeah. especially the 40 meter data. 40 meter data is pretty small in comparison with these two projects.
You know,
It's important enough.
One antenna versus
Yeah.
120. So, yeah.
Well, you've got to remember too, there's data from when you're doing cross correlation.
So that's what I'm saying.
So there's each antenna with all the others.
Yeah.
So it goes like
Yeah,
n
I'm
squared.
actually doing a little presentation tomorrow. It's going to talk about that very issue. So that's why that's part of my last here, how you're doing it.
Yeah, with the, so we try to have it in separate areas. And now with the UPS, our power is more reliable. We don't have things go down and risk, you know, funny voltages coming in. It'll just, it goes through the UPS, so it's, we don't have to worry about brownouts or anything like that. So we sleep better at night.
And the guys whose work is stored on it probably sleep better at night too.
Yeah, that's true. Yeah, our power has been so unreliable here that we had motor generators. You walk by one at the base of the stairs inside the 40 meter telescope, there was a quiet one over there on the left. We ran that one for many years because the utility power was just so unreliable. We in fact have one right behind us here in the little room over here is a motor generator set for this building. But we haven't run it for 40 years, almost 40 years now.
How many watts are you pulling in all this?
I don't know.
There's a lot.
Yeah, there is a lot. I just don't know. I don't know the answer to that. I can. Morgan, who came in this morning, he would know because he did a power budget for us. I just don't really know.
The only reason I'm asking is that it's an obvious question, but that's supposed to be your 500 watts, and your power supply was only 300 watts.
Yeah. Well, that's it.
Okay.